got walnuts in them.
Okay, so yeah, today what I'm going to be talking about is longest increasing subsequences of random permutations. So let me just get the definitions out of the way. So random permutation, which will go by the name of pi. It's just going to be random ordering of 1 through n. And for this permutation pi, I'm just going to write it as pi being drawn from Sn. This is a random permutation drawn from the symmetric group on n elements, which is just a set of all permutations. Okay, so uniformly random permutation. For example, right, so if pi is drawn from S10, then pi might look like the following. 7, 3, 6, 9, 2, 5, 8, 10, 1. Okay. And what?
You might need to use commas if you get up to S10. Is it 1, 0 or
1, 0,
yeah,
10.
Yeah, you said 10 once.
Okay. And the main quantity that I care about, this is fine for everyone, I assume. Okay, is going to be LIS of pi, which is the length of the longest increasing subsequence. Longest. And I'd like to contrast this with what I did in my talk. So when I was giving my theory lunch talk, I was talking about random words. And a random word, you'd have everything be a letter, which is sampled from some probability distribution independently. In particular, your word might have the same letter multiple times. But yeah, the key difference here is that our permutations, no number appears more than once. And furthermore, back then, in my talk, I defined, a weakly increasing or strongly increasing subsequence. None of that matters here. There's only one natural way to define longest increasing subsequence. For example, in this permutation pi, an example longest increasing subsequence is 3, 6, 8, and 10. And so we say LIS of pi equals 4. Okay, everyone good with that? Yeah, so the most classical of or classicalist of all results about LISs of permutations is this very old result from 1935 due to Erdős and Szekeres. Szekeres? Who said that? Is that how it's said? Okay, cool. Which says that every permutation. Oh my God, all these are terrible. It might be. Yeah, they're both black though.
Which one is black?
I already have black. Erdős and Szekeres, which said, is this one okay?
Better.
Okay.
Now you've already got green up there with the word every, so you should switch.
Switch to black.
Sorry.
Okay, cool. Which says that every permutation pi in a symmetric group has a longest increasing subsequence of length at least, does anyone know? 1/2 square root n?
Just square root.
Choose square root.
Erdős-Szekeres says that the
Square root
longest
of n minus
increasing or
1.
decreasing is square root n, so by symmetry it should be like 1/2.
Yeah, so the correct answer, of course, is that every permutation in pi has the longest increasing subsequence of length at least 1. But it's exactly what you were saying, which is that you have to say it's not just LIS of pi, but LIS of pi or the longest decreasing subsequence.
The or comes next, right?
Yeah, I'll put the or in a second.
Yeah.
For example, longest increasing subsequence, obviously, of n minus 1 all the way down to 1. There's no increasing subsequence of length 2 in this one. So this has longest increasing subsequence of length 1. So yeah, this statement says every pi has LIS of pi or LDS of pi where this is the longest decreasing subsequence, at least, let's say, root n minus 1. Something like that, basically root n. Okay, this is like a famous result. You can prove it by the pigeonhole principle. It's really simple.
Is that tight?
Yeah, that's okay. So I think you can do something where like, yeah, every root n blocks are like decreasing, or let's say increasing, but then all of them are decreasing.
Oh, yeah, I see.
It's like you have to add it.
Yeah, so it's like 5, 4, 3, 2, 1, 10, 6.
Yeah, exactly that.
So, John,
Yeah.
if you said that the LIS was, if I told you a subsequence and I said this is the longest increasing subsequence,
Yeah.
can you quickly verify it? I mean, you can write dynamic programming, the algorithm that will do it.
Yeah.
Can you do it fast?
So,
Is there a certificate?
yeah, I guess,
What's the question?
So if I told you that 3, 6, 8, and 10 were, I claim that 3, 6, 8, and 10 are the longest increasing subsequence out here.
Okay. Can you verify faster
yeah,
than
so at least what I will show you is an optimal algorithm for computing LISs. But yeah, I don't know if there's a way to prove, and it works in like n log n comparisons. I don't know if there's a way to prove it in like linear number of comparisons. Okay, so this is worst case, and what we are interested in is the average case. Okay, so the average case problem is going to be what is, of course, the expected length of a random permutation, or the expected length of the longest increasing subsequence.
And you have to run the algorithm like on the other part.
I mean, linear time would be fine.
Yeah, linear time would be an improvement.
Wondering whether we can do it in linear time.
Yeah, but I think you cannot have anything faster than the op. Like you have a speed of 2. Let's say that the candidate is in the half. You still have to run the algorithm on the right half.
Oh, no. Linear in the entire sequence, I'm fine.
Yes, but it will be M again for doing it. The optimal algorithm is M again, right?
Yeah, for doing.
Yeah. So how can you?
But it could be-
You don't know. That's for finding.
But it could be that I use a large amount of computation to produce a certificate, which you can easily check.
Oh, sure. But my question is how? Okay, but
That
from
could be a big
only.
certificate, right?
But from only like a claim, this is the best thing. You cannot infer anything about the algorithm part, right? So that's the matter.
I mean, there.
The certificate might be something other than sequences.
Yeah.
Okay, I didn't consider that, but sure.
Yeah, so I think it's an interesting question. I don't know if any work has been done on this. Yeah, so the average case complexity is a problem that goes by something called Ulam's problem, or Ulam, I don't know. What? Oh, cool, yeah, Ulam. And the question is, what is, and I'm going to write this as L sub n, script L sub n, which is defined to be the expected length of a random permutation of its LIS. And Ulam phrased this problem in 1961. It was around for a while, like 15 years before anyone actually solved it.
John, so just from the previous thing, the asymptotic, I mean, you have a lower bound, so that's the correct asymptotic. So 1/2 sort of then just from.
Yeah, so fact, L sub n is at least root n over, or n minus 1 over 2.
John,
Yeah.
So in this model, do we have a concentration just because of Azuma or something?
Yeah. There's a simple zoom as,
Martingale or something?
yeah.
You're saying half the time it's the longest increasing subsequence in the one? Gotcha.
Yeah, let me just write it out very quickly. This fact just is because if we look at the permutation pi sub reverse, which is equal to the reverse, pi n minus 1, all the way up to pi 1, then the longest increasing subsequence of this thing, well, this is just pi backwards. So this thing's longest increasing subsequence is the longest decreasing subsequence of pi. And hence, the expected LIS of pi is equal to the expectation of LIS of pi plus LIS of pi rev over 2. Yeah, and we know that one of these will be at least root n minus 1. Okay, so this is at least root n minus 1 over 2. Okay.
You could add a half to that lower bound because the other one's at least 1. Sorry.
Yeah, actually, I mean, there's a simple way to get this lower bound. What this theorem actually says is that like the product of these two is basically n, and so there's a way to use that fact to get this all the way down or up to root n. Okay. So that's a lower bound, and there's an easy upper bound actually. Which I won't prove to you, but it's an easy fact. You can just do this with like binomial coefficients and I don't know, Chernoff bounds and things like this. That L sub n is at most like order root n. Yeah, and the limit as n grows very large, there's a simple argument that will give you an e in front of this. And so, you know, we have an e over there, and we have a 1/2 here, and the question is, what is the right answer? Okay, and this right answer was proven in 1977, independently in 2 different works. One from Russia, which I don't think made its way over to the US for a while, by Vershik and Kirov, and then one in the West by Logan and Shep. And they showed that L sub n tends towards 2 root n as n approaches infinity. Yeah, actually the right way to phrase it, of course, is to look at the limit of L sub n divided by root n as n goes to infinity, and so that thing approaches 2. But yeah, basically the highest order term in this number approaches 2 root n. Okay, and this was for large n approaching infinity, but following this, Vershik and Kirov, again, same people as this, in 85, and again in Russia they were doing this, but in the West, Pilpil in 90, showed that in fact, although this thing happens in the limit, you can actually give an upper bound for all n of 2 root n.
No lower order term?
No lower order. It's a very nice 2 root n. And this is what I'm going to show you today. Okay. Right. Yeah. Actually, yeah. So you'll see. Well, as you'll see, hopefully you'll like the proof. It's like elegant, nice combinatorics. It turns out that like the really difficult direction of this statement is the lower bound, showing that there always exists permutation, or sorry, an increasing subsequence of size around 2 root n. And so far as I know, it's still like an open problem to give a lower bound on this for all n that is like 2 root n minus some nice function. So this is something that people, I think, still do not know how to do. Okay.
Just learn how to do like 2 minus epsilon.
Yeah, for any epsilon you want, there's an n that's sufficiently large that you know, this thing is at least 2 root n minus epsilon. But you'd really like something like 2 root n minus something a little o of root n, some nice like log n or something.
So, John, do you happen to know what the constant was like in the Chernoff bound proof?
Yeah, so this thing, what you get out of this proof is a statement that L sub n over root n is lim sup as n approaches infinity is at most e. So like an e root n. And you know, I'm not just showing you this proof because like I'm obsessed with constants or anything. It turns out when we go to the setting that Ryan and I care about, generalizing all this to the quantum stuff that we need, like this proof just doesn't work anymore. So we really need whatever style of proof that they use here. Okay. So, right, any questions about this? Or I will go on to...
So is the easy proof really easy? Like,
the easy proof is, yeah, I would say it's not too hard. I mean, it's like 1 page, doesn't involve any new math that you haven't seen before.
Like a homework problem?
Yeah, let's say that. I mean, it could be done on a homework problem with maybe some hand-holding.
You say from the proof that we have the square root n minus 1 over 2, there's probability at least 1/2 the longest increasing sequence to at least square root n, and then you apply concentration bounds, right? Somewhere.
Well, that will give you a lower bound. But this thing is an upper bound. Yeah. Okay. Any other questions? All right. Okay, so now I'm going to introduce this RSK algorithm, which most of us have seen before many times. But yeah, I'll do it again. So the RSK algorithm is, well, I'll just give you an example run. So I get to click on these numbers and choose a permutation, and it will feed it into the RSK algorithm. And what it looks like is as follows. Let me just click around randomly. So I pick, the order I do it picks the order of the permutation. So this is 4, 6, 5, 8, 3, 7, that was a permutation. And then the RSK algorithm actually output, maybe you've seen my talk and I just said it outputs one diagram. It actually outputs two diagrams. Okay, and yeah, so what are these things? Let me give you some terminology. It outputs two things, which, you know, they're boxes or arranged into rows. The main terminology is a Young diagram. So a Young diagram is just one of these arrangements of boxes. So some boxes that look like this. And typically we like to name these Young diagrams lambda, and we care about the row lengths. So we name the row lengths lambda 1, lambda 2, and lambda 3. So this lambda 1 is equal to 3, lambda 2 is 2, and so on. And the fact that it's a Young diagram just tells us that the lambda i's are non-decreasing. So lambda 1 is at least lambda 2, and so on. And that's what a Young diagram is. And a Young tableau is just, and I'll give it a name T, is one of these diagrams. It's a lambda, but it has numbers in it. Okay. Okay, so what this algorithm does is it takes in a permutation and it outputs two Young tableaus. And it looks like the two Young tableaus have the same shape, as in like, yeah, their shape is the same. And yeah, that always happens. So let me explain to you how these Young tableaus are created. The second one is actually easy. So I'm going to do this again. I want you guys to pay attention to the second one, and then I would like someone to tell me how to create the second Young tableau. The first one is more difficult. Let me go. Or at least, how do I pick the numbers in the second one? Right. So I do this step by step, and at every step I add a new box. And on this side, whenever I add a new box, let's say it's the ith box, then I just put the number I in that box. Okay, so let me do this one more time. Okay, so notice I have boxes appearing, and every new box comes with a corresponding number in it. All right, so this box came last, it's the 10th box. Okay, everyone good with that? Now, I haven't told you how the boxes appear yet. Well, that's fine. Okay. Yeah, actually, let me just tell you how the boxes appear. No, that's the next part of the lecture. Okay, so yeah, the way this works, let me start over. add a few numbers into the diagram, and now consider what happens when, say, I add the number 7. Okay, so the way I'm going to add the number 7 to this box, I'm going to do something called an insertion. And what's going to happen is I'm going to scan the first row with the number 7, and I'm going to find the first box in that row with the number bigger than 7. So I'm going to go left to right, and I'm going to stop in the first box that I see a number bigger than 7. In this case, it's 9. And what I'm going to do is I'm going to take the 9 out of that box and put a 7 into that box. Okay? So let's do an example. Yeah. Okay, so I took a 9 out of the box, and then I put a 7 into that box. And now the 9 went somewhere. I'll explain that in a second too. So there's a second rule. Let me see if I can undo the last insert. Yeah, so I'm trying to insert the 7. Basically the rule is if there is no number that's bigger than the box in this row, then I create a new box at the end of the row. And I put the number into that box. So for example, if instead of the 7, I would have put a 10 in, then you would go left to right, you'd see that none of these numbers is bigger than 10, so you create a new box here and put a 10 in there. Okay? And now the final rule is that, let's say I put the 7 back in there. So I put the 7 in here, I take the 9 out, I put the 7 in its place, and then I do something called bumping the 9. And when I bump the 9, I just insert it into the next row. Okay, using the exact same rule. So I'm going to insert the 9 into this row. I'm going to scan left to right, see if there are any boxes bigger than 9. I see that there are no boxes bigger than 9, so I'm going to create a new box here and fill it with a 9.
Okay.
Yeah, let's do.
I'm sorry, can you undo this insertion?
Can I do what?
Can you undo this?
Yeah.
And so if you like add the 2, then it will be 2, 5, 9, and 3, 4, 6.
Yeah, let's see. If I add the 2, then 2 will be smaller than 3. So I will place the 3. Then I will insert the 3 into here, which is smaller than 4.
Oh, okay.
And so yeah, let's see what happens.
Okay.
Okay. So let me write this in words. Okay, so insert. If you want to insert a number A into your Tableau T, you scan the first row, left to right. You find the first B greater than A. So you find the first letter that's bigger than your letter. You remove B from the cell, and you replace it with A. And then we say here that B is bumped. And then you insert B into the next row. Recursively using this procedure.
2.1, there is no such B, just a kind of field.
Yeah, if there's no B, you create a new box at the end and put B inside. Okay, so are there any questions about this algorithm? Okay. Yeah, so this algorithm, every time I insert a new letter into this Tableau, it will create a new box somewhere and put that letter in here. And then at the same time, in this Tableau over here, I'll look at what box was created there, create the exact same box over here, and then put the step number that I'm in. Okay, and so this is what we call RSK applied to pi, and it's going to output two young tableaus, which I'm going to call P and Q. P is called the insertion tableau, because that's where I insert everything into. And then Q is called the recording tableau. Okay, Q records the growth of the tableau. Okay. And one other thing, I'm going to, so these tableaus have a shape and that shape is just given by Young diagram. When I say the shape, I just mean the Young diagram that you get when you delete all the numbers. Okay, so this would have shape like 3, 1, 1, 1. And so I'm going to denote this as SH, shape of the RSK algorithm. Pi, and this gives me some Young diagram length.
Hold up, shape is this pair.
Pardon?
What's shape?
So shape is, you output 2 Young tableaus, and they both have if you look at them, they always have the same shape. That shape is given by Young diagram.
Okay.
So
That's a lot.
this is the Young diagram here. Okay. And let's write down one more property of these Young diagrams that we get. So these Young diagrams that this algorithm outputs always have a property that they are something called standard. What do I mean by that? So the Young tableaus. A standard Young tableau is just one of these Young tableaus that we get, subject to the constraint that if you look at any row or any column, the numbers are always increasing. So the numbers increase left to right. Left to right. And top to bottom. Okay, well, let's see why that is. Let me pick a good. Okay, so I'm gonna, just to show you why these things are always standard, let me do an example with the permutation 4, 7, 3, 6, 2, 5, 8. Oh my god, I made a mistake. Let me undo. 4, 7. So this one's standard. Basically what standard means is that, every time, whenever I add a new box here, I'm always kind of growing outwards. I always add a new box kind of to the right of other boxes and below other boxes. And so this thing, I'm always going to, whenever I add a new box here, it will always have a bigger number than all the other boxes that I've seen so far. Meaning that this one will always be, to the right and below previous boxes, it will always have a bigger number than them. And so it's always going to be a standard Young tableau. Okay, let me again try this. 3, 6, 9, 2, 5, 8, 10, 1. Okay, right, when I grow this Young diagram, I always add new boxes to the right and below. It kind of grows, it always grows in this direction. And every time it grows in this direction, I add a new box. First 1, 2, 3, 4, 5, 6, and so on. And that means, this is the definition of it being a Young tableau. These numbers increase, these numbers increase, these numbers increase, and so on. I don't know if that was very clear. Anyone confused about that?
They decrease, right?
No, they increase.
Don't you have for each row you have a technical number? That's the number you find out.
Oh, no. When I say the numbers, I mean the numbers in the boxes.
Okay.
Yeah.
Yeah,
Yeah, not these. Yeah, the row lengths will always decrease, or non-increase at least. But the numbers in the boxes will increase going down and to the right.
Why do the row lengths not increase?
That's something that's slightly non-obvious. But yeah, let me...
Sorry, what was the question?
So why can't I have the second row being longer than the first row?
Like that property in the induction.
Yeah.
I mean,
Like the property you just said right now.
yeah, let's do an example and see why it doesn't happen.
I guess every number that got pumped was because of some other number that was kind of there.
Yeah.
Okay. That's not
Yeah, somehow, like, if you think about it for a second, basically you're asking, like, will you ever get something that looks like this?
Yeah, even
Right.
to get the numbers. Yeah.
But yeah, and this will, I guess, never happen, because for you to get in this spot, I mean, how would you even get in this?
When do you increase the length of a row is if you have something that's longer than all the guys in that row, right? But since you're you increase top to bottom, that means the longest guy in the second row is larger than the longest guy, and the largest guy, bigger than the biggest guy in the first row, right? So if you can be appended to the first row,
No, it's the other way. I mean, in the long.
Look at the two up there. It's smaller.
You said it wrong, but I think the idea is right.
Okay, I'll have to think about it.
Yeah, it's not a difficult property of the algorithm, but.
I still don't understand the numbers in the black boxes.
Yeah, so the number in the black boxes mean the following. Do you understand the algorithm that I gave for creating this? So what these numbers will, every step that I insert something into here, I'm going to create a new box. And at step I, I'm going to create some new box here. And then what I'm going to do here is create the same box. And if it was step I that I created it in here, I'm going to put the number I here.
The time the box.
Okay, so here, let me do this again and just watch both at the same time. Whatever box appears here will also appear here, but with the next number of the sequence. Yeah, just yeah, check this out.
See it?
Right?
Yeah.
So the time it was created, right?
Exactly. Okay, we good? Okay, any other questions about? Okay, and hopefully we all believe that this thing is a standard Young tableau. Let me also prove to you that the thing on the left is a standard Young tableau. For example, so the way you'd prove that the thing on the left is a standard Young tableau is just by induction. You'd show that every step is a standard Young tableau, and then whenever I insert a new number into it, it maintains the fact that it's a standard Young tableau. So let's just imagine that at some step we were at this Young tableau. One, 5, 8. 2, 6, 9, 3, 7, and then we inserted the number 4. Okay, so this algorithm is going to go left to right and try to find the first thing that is bigger than 4, and it's going to put 4 here, right? And I want to claim that this always at least maintains that the first row is always increasing. And this is just because if I put it here, so originally 5 was here, I'm about to put 4 here. 5 is the first thing that's bigger than 4. So that means everything before 5 is smaller than 4. So at least if I put a 4 here, it won't disrupt the standard property from it and to its left. Right? It will always be bigger than everything here. Similarly, because 5 is the first thing that's bigger than 4, then that means everything to the right is bigger than 4. And so if I replace the 5 with a 4, then yeah, this will be smaller than this. And so if the row started off being sorted, then it's going to remain sorted. Okay? That's only one part though. You also have to show that this stays increasing. But you know, 5 was smaller than 6, and 4 is smaller than 5, so 4 is smaller than 6. Okay, so that at least shows that this row and this column are both sorted. But now there's another step of the algorithm, right? I took out the 5 and I have to bump it into the next row. And by the exact same idea, when I insert 5 into this row, so I'm going to go across, I'm going to find the 6 and replace it with the 5, then at least this row is going to remain sorted. Okay, because I'm just inserting into this row. And now I basically have to show you that at the very least what I get here is, when I do this row, that I don't break sortedness in this column. Right. And why don't I do that?
Isn't it the exact same thing?
You're just doing it once again.
Yeah, but previously we showed that it worked. on this row and like below.
Oh yeah, so I guess 5.
Yeah, so
smaller.
exactly. So 5 can't go any further than this one, because why?
Because it would have something larger than it, something
Right.
larger than 5 below it. And so at least at that point you would insert it or sooner.
Yeah, so since you look for the first thing that's bigger than 5, and because we know 5 is here, so something bigger is here, then this is at least the first thing bigger than 5. And so either you put a 5 in here, but you can't do that. Okay. And that tells us that when I put a 5 in here, it's going to be bigger than before.
But what was the argument for again for that it was originally sorted?
Yeah, assuming that it was originally sorted. So this is by induction. Every step it maintains sortedness. Okay. So the end result is that is just to show you that both of these tableaus, the P and the Q, are both standard Young tableaus. Any questions about that?
No, I'm sorry, the last tableau is standard Young.
Yeah.
Right?
Both of them are.
The right one is just because they're always on diagram through it.
I mean, the right one that like grows out, and you always put the biggest number you've seen so far in the newest at itself.
Oh, I think the right one is easier.
Yeah, the right one's the easy one. But do you get the left one?
Yeah.
Okay. Any other questions? Or any questions? Okay. So first, why does this thing pop up in longest increasing subsequences? We're looking at longest increasing subsequences of permutations. Why do we care about this algorithm? Well, this is because of the following fact, which hopefully some of you have seen before in one of my talks, which is that if lambda is the shape of this diagram that you get, so if lambda equals SHRSK of pi, then the length of the first row, which is lambda 1, equals the longest increasing subsequence of pi. For example, I don't know if you guys know this, but this thing is like maintaining, so as it computes this Young diagram, it also tells you the length of the longest increasing subsequence. And this word, it happens to be 4, and that's because this is 4. Okay, and the proof of this is not too hard. So in fact, like, yeah, this is kind of the natural algorithm for computing longest, or a natural algorithm for computing longest increasing subsequences.
Very greedy. I mean, if I just focus on the first row.
Yeah.
It's very greedy. It's like, oh, I'll try to maintain the lowest, longest
Exactly.
subsequence kind of thing.
Yeah. So this thing is, it's like a natural dynamic program that you would write. And you know, sometimes you write like a recursive program, and then you want to turn it into a dynamic program by like memoization. This is the data structure that you would use for the memoization. Okay.
Sorry, what is the worst complexity of this algorithm around n squared?
This algorithm is n squared, but if we only care about the first row, we're computing the longest increasing subsequence, then it's n log n. Just because like if I want to find the first thing that's bigger than me, I can always just binary search. Okay, but yeah, let's prove that this is this. So I claim that let's do it by induction, as always. We insert n letters, but let's imagine after step I, what happens. So after step I, let's just look at the first row of the the insertion tableau. So the first row is going to look something like this. It's going to be a ton of boxes. Let's say this one has the letter A1, A2, A3, A4, and so on. All of these are the numbers in the first row. And then I claim that at this step, AK is going to be equal to, so the number in the kth box, it's just going to be the minimum over all subsequences S of length K, subsequence is S of pi 1 ... length k of the rightmost number. In S. Okay, so in other words, at step I, what does this data structure maintain? Well, at step I, I've only inserted into my data structure pi 1 through pi I. So first I'm only my data structure only records something about the first I letters of my permutation. And the kth position of this data structure just says, let me look over all subsequences of the first I letters that have length k. And I just want the one that has the smallest rightmost number. And of course, the rightmost number of a subsequence is like the largest, also the largest number of the subsequence.
Minimum increasing subsequence or minimum subsequence period?
Increasing, most definitely increasing. Thanks. And let's do a proof by picture. Okay, so this I will also prove. Basically everything here is done by induction. Let's say at the first step, well, let's say we just do this with like pi equals, I don't know, 2. So pi is length 1. That's not actually a permutation of 1, but whatever. It's just some letter. And then my insertion tableau will just be the number 2. Okay, so I only have one subsequence, and it ends in the number 2. And so this has length 1, so the first box will, it looks over all subsequences of length 1. What do they end with? It's a 2. Okay. A couple more easy examples. If pi is 2, 3, then I'm going to look at 2 and 3. So the first cell, if I insert a 2, then I insert a 3, which goes past the 2. The first cell says that of all subsequences of length 1, which is either 2 or 3, the smallest one is 2. And the next cell is I look over all subsequences of length 2. There's only 1, and it ends with a 3. Okay. But more generally, I mean, let's imagine that pi, it equals pi 1, pi 2, all the way up to pi, let's say I minus 1. So these are the ones that we've inserted before. And let's say pi sub I is the number 7, and so on. Then the first row of my tableau might look something like this. 1, 2, 4, 6, 8, 15. And at step I, I'm going to try to insert a 7 into it. Okay, so let's assume by induction that this is what I did. This is what I got after step I minus 1. And every cell contains a minimum over all increasing subsequences of length k of the rightmost number in that subsequence. Okay, and now I'm inserting 7, and I'm trying to figure out, let's see what we would do to this data structure if we wanted to maintain this. Okay, so first, I'm inserting 7 into my word. So I could put a 7 here, because I know that I have a subsequence of length 1 that ends in a 7, which is just this subsequence. But I also know that's stupid, because 1 is smaller than 7. So I should just keep my 1 there. Right? Now for the next cell, I could say, well, let's look at, do I get any good length 2 subsequences here? And indeed, I know that there's a length 1 subsequence here that ends in a 1. And then I could follow that with a 7 to get a length 2 subsequence that ends in a 7. So I could stick a 7 here as well. But, 2 is smaller than 7. So I don't need to put a 7 there. So if you repeat this argument, the only time that you will ever need to update this data structure is at this point. Because, this tells me that there's a length 4 subsequence in this word right here that ends in a 6. That means that there's a length 5 subsequence here that ends in a 7. And that 7, is smaller than 8. So I would like to replace the 8 with a 7. Okay, and that's exactly what the RSK algorithm does. And of course, maybe going back to here when this was an 8, should I update to 15? Well, no, because the smallest length 5 subsequence here ends in an 8. So there's no length 6 subsequence here that ends in a 7. Okay, so the only thing I want to update is this. And that's how the RSK algorithm works. Okay. Any questions about that? Cool. All right. So this shows why the RSK algorithm appears in this context, or at least why one might consider it. Oh yeah, so I should mention, if you were to run this RSK algorithm, the number of comparisons, so if this was an algorithm that you might like to run for computing the longest increasing subsequence of a string, it would use n log n minus log n minus n log n plus order n comparisons.
The binary search.
Yeah, using binary search at every step. And it turns out that
This is just for inserting in one row or just computing the entire thing?
yeah, so if I only care about the longest increasing subsequence, then I ignore rows 2 through whatever. So if I only did this thing, then this would give me this many comparisons for computing the longest increasing subsequence. And this turns out to be optimal up to the big O in the end. So there's a lower bound that's exactly n log n minus this plus that. Yeah, and if you only care about this first row behavior, and you ignore the rest of the diagram, this thing also has a name called, a patience sorting. So it turns out there's a sorting algorithm that's based on this idea. Like a normal sorting algorithm, like quick sort or merge sort. Okay.
Is there any succinct representation of the other rows?
Yeah, there is a succinct representation, which maybe if you've seen my talk, you've seen this, which is that lambda 1, for example, lambda 1 plus lambda 2 is equal to the length of the longest disjoint union of 2 increasing subsequences. And then you repeat that for lambda 1 plus dot 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 plus lambda k. Fortunately, we will not need that.
Sure.
That's actually a much more difficult. This is like ridiculously easy. That's very difficult. I actually don't know the proof of that.
Is there still some sort of interpretation for like 8Ks on the second row? It's just
For the letters on the second row.
It's like a lot higher to state.
I don't know actually.
What's the question? Yeah, that's kind of what I was asking.
Oh, is that what? Yeah, I don't know what the interpretation of the letters on the second or third or fourth row.
I mean, that's like the smallest tail end of like.
Yeah, so it's actually not. Well.
So it's exactly this. Consider all the subsequences that have longest increasing sequence I and longest decreasing sequence D, and over all of those, minimize the maximum level.
Yeah, that's what I was thinking.
It's exactly that.
Maybe it's something like that. Yeah, I don't know.
Okay, I'm claiming it's exactly.
No, if it's that, that's awesome. Yeah, write it down and send it to me. I'd like to know
because
this.
that's true. I mean, to me it seems like maybe you want to define your Young diagram just explicitly that way, and then just say that okay, fine, because of that we have this increasing property of the rows and columns, and
Yeah,
that's it.
the increasing is obvious from that.
Yeah, I mean, there are other reasons you want to define your Young diagram or RSK algorithm in this manner.
Because it tells you the runtime, I guess?
No. I mean, oftentimes the computational nature of it is necessary.
Okay.
Like the exact algorithm that it uses.
Okay.
Anyway. Okay. So that's the RSK algorithm. This is why we're at least considering it. But now the question is like, why is it useful? Because I've just given you like a complicated algorithm for computing some property. But I haven't told you like, how is it useful for determining the average longest increasing subsequence of random permutation? Or, I haven't told you why should I look at the algorithm beyond just the first row? Because the first row seems to get us everything that we want. And the reason why it's so amazing, this is why combinatorialists love this thing, is because it's of some property called the RSK correspondence.
Isn't it combinatorial?
What? Wait, what?
Isn't it combinatorial?
No, realist. That's right. Yeah, combinatorial.
Okay, I'll let you guys find it out. Okay, so called the RSK correspondence. And, you know, what I already showed you was that, well, I'll just state it. Okay, so what is the RSK correspondence? It says that the RSK algorithm gives a bijection. Between. So it takes in a permutation pi in the symmetric group, and it gives a bijection between this and pairs of Young tableaus, standard Young tableau, P and Q, they have n boxes, standard Young tableaus with the same shape.
So
I didn't expect to get oohs and ahs of that,
But so this is the label, like you don't like. So the P and Qs have numbers.
yeah. In other words, I put in a permutation, I get a pair of these things. This map is actually a bijection.
Count the left.
Exactly. Then let me do the proof of this. The proof is actually very nice.
Okay, there is indeed evidence for both possible.
What?
Everyone.
There is evidence for both combinatorial and non-combinatorial.
Okay, cool.
I was such a disappointment when you argue with someone about a pronunciation. I don't understand what the right-hand side says.
Yeah, so the right-hand side is basically the things that this algorithm outputs. So this algorithm will output two standard Young tableaus, P and Q. They always have n boxes because I had n elements.
Oh, I see.
And they have the same
shape.
shape. Yeah, same shape. Okay. Okay, so the proof, well, there are two directions. In the proof, I have to show it's like injective and surjective or whatever. The first step is just to show that this algorithm always maps, you know, permutation into one of these P's and Q's that have these properties. But, you know, I've already shown you this. This is what I spent earlier in the lecture showing. Check. So now I just have to show that, you know, RSK is invertible. You had a question?
No.
Okay. So let me show you how to invert the RSK algorithm. I'm going to do this pair as my example. One, 5, 8, 10, 2, 6, 9, 3, 7, 4, and 1, 2, 5, 9, 3, 4, 8, 6, 7, 10. So this is my P, this is my insertion tableau, and this is my Q, my recording tableau.
Do you just go in reverse order of each row? And count the time or something?
No, so there's, what I'm going to do, yeah, so what I want to do, given these two, is find the find the permutation that RSK would map to these two, right? So what I'm going to do is I'm going to show you how to undo one step. So the question I want to answer was, what was pi 10?
But you have, sorry, don't you have like the whole operation? It's just a few lists of the rows, but like
So yeah, what I want to actually find out is what is pi 10, and then what did these two things look like before I inserted 10? Okay.
Pi 10 is 1.
Yeah.
So we all know what pi 10 is. Wait, what's pi 10?
According to
Yeah, according to that, it's 1.
That's kind of cheating, right?
Yeah.
No,
So-
you can see you just increase the length of the last row, the last step, and step 10, right? Now you just have to kind of.
Exactly. I mean, I'll carry this argument out right now, but it's exactly what you're saying. So what do I know? In the last step, I know that a box was created here because of my insertion tableau. So my goal is to find what did P and Q look like before I inserted a 10 into this tableau. And I know because this is where the last box appeared, that before I inserted a 10, Q just looks like this. 1, 2, 5, 9, 8, 7, 6, 4, 3, 6, 7. Right, this is maybe Q prime. What Q looked like before I inserted the last number. So now I just had to figure out, what did P look like before I inserted the last number? Well, I know in the last step, when I inserted the last number, the last thing that happened was this box was created with a 4 in it. And the only way for this 4 to have gotten here was that it used to be in this row, and it was bumped down here. Okay, so in the last step what happened was this 4 was here, and the only reason it got here was because it was inserted here, and the reason it was inserted here was because it got bumped from this row. But only one number here could have bumped a 4, and that's a 3. So if there's a 4 here, and I inserted a 3 here, then I would replace the 4 with a 3 and bump the 4 down. Okay? So now how did the 3 get inserted here? Well, it had to be bumped from this row, and there's only one number that could have bumped it, which is 2. So that means there used to be a 3 here. What? Yeah. And 2 was inserted into this row. And finally, the only way that 2 could have been inserted into this row was that it was bumped from this row. And the only number that could have bumped it was a 1. Okay, so this is a sequence of bumps and inserts that happened when I inserted my last number. And I know that my last number was a 1. So pi 10 equals 1. And now I'm one step earlier in the algorithm. Okay, that's exactly what we see up here. The last letter was a 1. So that got me the last letter, and now I can just repeat this procedure and continually unbump letters until I get the whole string. Okay, and this shows that you can indeed invert the RSK algorithm. Okay, any questions about that?
So is it always true that your inversion is some concatenation of permutations of the rows?
I would guess no.
Because it shows this example.
Yeah, I would guess almost certainly no. But this is like a small, n equals 10 example, and it might just be because of that. Okay, so any questions about the proof? Any questions about the statement? Okay. All right, so let me now tell you the consequences of this statement.
The number of young tableaus is like square root n factorial.
Yeah, something like this. So I'm going to define for every shape lambda, the quantity dim lambda, which is just equal to the number. So the lambda here is a Young diagram, and dim lambda will be the number of standard Young tableaus of shape lambda. Okay. Then a corollary of the RSK correspondence, the corollary that we will care about, is that the number of permutations, so if I look at the set of permutations pi in Sn, such that the shape that the RSK gives to them, RSK algorithm gives to them, equals lambda, the size of this set is exactly equal to, well, in any one of these permutations is mapped to a P and a Q of shape lambda. And we know because of this bijection that every pair P and Q occurs once. So the size of this set is exactly equal to dim lambda squared.
So if
Yeah.
not given the pairs of P and Q, if you only give P or only give Q, can you go back to the...
No, yeah, that's the whole point, yeah, because this is saying that if I pick P, I can put any Q here, and there's always a different permutation that will match it. Okay? And similarly, if I want to consider every permutation, pi, that gets mapped to some shape lambda, I just have to consider all standard Young tableaus P and standard Young tableaus Q of the same shape. Okay? In other words, the probability, if I pick a random permutation pi, the probability that pi from Sn, that its shape is lambda, well, there are exactly n factorial permutations, so I divide by n factorial. And the probability that I get lambda, I know I get 1 for every guy in this set. So this probability is exactly equal to dim lambda squared.
I think that is something related to representation theory.
Yes. So this right here is called, this distribution on Young tableaus, Young diagrams is called the Plancherel distribution. Distribution. I should mention that, it's called Plancherel. It's similar, if anyone knows the Plancherel formula from Boolean function analysis, they're kind of related. This is like a natural object that you could define in representation theory, not knowing about RSK, not knowing about permutations. Every finite group has something called the Plancherel distribution associated with it. Just so happens that for the symmetric group, this is the form that it takes. Yeah?
Is it, the shape is exactly equal to lambda? Lambda are just equal to the shape of lambda.
Pardon?
In your correlation here, the shape of the RSK from the permutation is equal to lambda, or is equal to the shape of lambda, or are those things the same?
Oh, so lambda is a Young diagram. So if I give you a Young tableau, it's a diagram with numbers in it. The shape is going to be what happens when I delete the numbers.
The diagram has no numbers.
Right.
Okay.
Yeah. Any other
So the
questions?
diagram is basically equal to the shape of the row.
Yeah, the diagram is what we use for a shape. Okay. Any other questions? Okay, so with all this said, I can now give you the proof of, let me write one more thing then. So this says that if I draw, so I'm going to use Planch sub n for the name of this distribution. So if we do everything then, we get that the expected, if I draw a random Young diagram, lambda, from the Plancherel distribution, n, and look at the length of its first row, then we saw that the length of this first row is equal to the longest increasing subsequence of the permutation that gets mapped to lambda. So this expectation right here is exactly equal to the expectation of a randomly drawn permutation pi of the LIS of pi. Okay. Yeah.
Just a quick question. When I look at all the pies that have such that shape of RSK of pi equals to lambda, is there some other way of interpreting diagonal plane? Are they the same conjugacy class or something?
Yeah, there's some sort of.
Is there something I can directly see instead of just looking at the sound of them to see if they'll have the same shapes?
Yeah, there's something called Knuth permutations or something like that, and whenever you do this, it will maintain the shape.
Okay. So it's like the invariant sense.
Yeah, if the word semigroup means anything to you, apparently there's something involving a semigroup here.
Okay.
I don't actually know what that means myself, but
just a group without inversions.
Okay, cool. Yeah, but there's something like that. Sure. But it's still very non-obvious.
Yeah, nothing like that. Yeah, nothing that I can see.
Yeah.
Right away.
Yeah. If I give you two permutations and I ask you, do they have the same lambda? I don't know any better way than to just run RSK on both. Okay. Any other questions? Does this make sense to everyone? Okay. So let's go back all the way to the beginning and see what we wanted to show. The theorem that we wanted to show was that L sub n, which equals the expectation of pi drawn from Sn of LIS of pi, was at most 2 root n. So let me do the proof. What I'm actually going to bound is the quantity which I call delta sub n, which equals the difference of lambda n and lambda n minus 1. So I'm going to try to telescope my series. And my goal is to show that delta sub n is at most 1 over root n. Okay, in which case, then L sub n will be equal to, L sub n minus L sub n minus 1 plus all the way down to L sub 1 minus L sub 0, which equals sum of I equals 1 to n of delta n. So at most, sum of I equals 1 to n, 1 over root I. And this just so happens, this is like calculus or whatever, to be at most 2 root n. Okay. Actually, yeah, let me stick this down here. Okay, so everyone's fine with this. Then delta n, I'm going to define L sub n minus L sub n minus 1. And the goal is delta n is at most 1 over root n. So at this point, knowing that you want to bound this quantity, it's almost just like you follow your nose. You don't do anything surprising. I mean, there's one clever aspect of this proof, but the fact that this took people like, 25 years to discover, it's kind of surprising. But I guess just no one knew that this was the right first step. But once you say this is your first step, then the RSK algorithm takes you where you want to go. Okay, so yeah, let's analyze this. Let's look at L sub n minus 1. By definition, this is the expectation of a permutation drawn from S sub n minus 1 of LIS of pi. Actually, let me rewrite this as you take the shape of the RSK algorithm applied to this and just look at the length of the first row. Okay? And I claim that this is exactly equal to if instead of drawing it from S to n minus 1, I drew it from the symmetric group on n elements and applied the RSK algorithm to pi, but only the first n minus 1 letters of pi. Right? I mean, I'm putting in n minus 1 distinct letters into the RSK algorithm. RSK, it doesn't know about the values of the letters, only how they relate to each other. So from its perspective, putting in n minus 1 distinct letters is basically the same as putting in a permutation of size n minus 1. Okay. In which case, delta n, the thing we're trying to bound, which equals L sub n minus L sub n minus 1. Well, L sub n, by definition, is just the expectation of a randomly drawn permutation of the shape of the RSK algorithm at pi, the length of the first row, minus, so that's L sub n, and now we subtract this off of it. And for any fixed pi, what is this quantity? It's exactly equal to the probability. Well, this quantity is 1 if and only if the very last step of the RSK algorithm added a box in the first row. So this whole quantity is just the probability over pi drawn from Sn that the last box added in RSK is in the first row. Okay, so this is a Plancherel distribution. Gonna miss the punchline. Okay. So the experiment we're doing is we're taking a random permutation, pi, mapping it through the RSK algorithm, and we get two diagrams of the same shape, P and Q. And can anyone tell me what I'm looking for in P and Q.
The last element is 10.
Exactly. So I'm going to look at the last box in the first row. And I'm going to look at the recording diagram and just say, is there an n there or not? Okay, so this event is a probability that Q has an n in its last box, in the first row. Okay, so now the magic of the RSK comes in. I can now give you like a precise formula for the probability that this happens. And what is this? Okay. So for this fixed shape, lambda, so first, one thing has to happen. It can't be the case that, for example, lambda looks like this. This can never happen because this n will be bigger than the stuff below it. So it has to be the case that this box actually sits outside. In other words, it has to be the case that lambda equals mu plus the box in the first row. Where lambda has n boxes, and I'll use this notation. Lambda has n boxes and mu has n minus 1 boxes, and they're both Young diagrams. Okay? So the number of such p's and q's that I get, which have an n here, is exactly equal to this part has shape mu. So this is SYTs of shape mu, because once I take out the n here, the numbers here are 1 through n minus 1, and they can go wherever they want, so long as they're standard. In other words, the number of q's I get is exactly dim of mu. And the number of p's I get, well, there's no restriction on p whatsoever, so the number of possible p's I get is dim lambda or dim mu plus the box in the first row. So in total, if I set this thing to be equal to star, then star is just going to be, well, you always have 1 over n factorial, and then the number of pi's that have this property is going to be the sum over all mu, which have n boxes, or n minus 1 boxes, of dim lambda, sorry, dim mu plus box, and times dim mu. Okay. Everyone good with this? This is like the one magic step, so there's nothing else magical that's happened today. This is it. Okay, so in other words, this RSK bijection gives me a very easy to detect event to know when this event happens. And it's exactly when I get an n here, and then I can easily count all the permutations where such an event happens. Okay, so the final step is just to upper bound this quantity by 1 over root n. And does anyone want to suggest? Any suggestions for what to do? Yeah.
If it was just dim mu times dim mu, that second part would be n minus 1 factorial.
Yeah.
So it's pretty close to that.
That's true.
That would give you 1 over n, so sometimes you have to show it's not more than root n times that.
Yeah. Yeah, so that's like exactly the right intuition. We're about to use stuff that looks something like that. I don't know, we have a sum, things multiply. There's like only one theorem you ever use when proving things. You use Cauchy-Schwarz, exactly. So exactly what you were saying. So let's rearrange this first before doing Cauchy-Schwarz. This is sum over all mu, which have n minus 1 boxes. And this thing, as we saw earlier, it's kind of most naturally paired with, dims, this has n boxes, it's mu plus box, n boxes. So this is naturally paired with an n factorial, whereas this thing is naturally paired with an n minus 1 factorial. So let's split it off that way. This is dim mu plus box times dim mu. And I'm going to split up this n factorial by first putting a root n here, then putting a root n factorial here, and then putting a root n minus 1 factorial. Okay. Next step is Cauchy-Schwarz. This is at most. Square root of sum over all mu size n minus 1 of dim mu plus box squared over n factorial times 1 over n. And then from the other part, I get a square root sum mu partitions of n minus 1 of dim mu squared over n minus 1 factorial. Okay? This is a probability distribution given by the Plancherel distribution over mu's of size n minus 1. I'm summing over all of them, so this is just 1. And this is like almost a probability distribution. If here I was summing over, this sums over like all lambdas, which are of the form mu plus box. If I just summed over all lambdas, this would be summing over every element of the Plancherel distribution. So, well, I'm just gonna, upper bound this by the sum over all lambdas, which are partitions of n of dim lambda squared over n factorial times 1 over n. And again, this thing is the Plancherel distribution summed over all the elements in the probability space. So this is a 1. And I get 1 over root n. Okay, so like, yeah, I mean RSK, it's like almost obvious what you do here, right? RSK gives you this magical bijection, and once you use this magical bijection, and you want to prove, I don't know, whatever statement we wanted to prove here, then you kind of follow your nose. Like you just look at what it gives you, and it tells you exactly what you're looking for.
So the only part where this becomes an upper bound is when you start using Cauchy-Schwarz.
Yeah.
And also when you add extra lambdas, right?
Yeah. These two. Although, like, yeah, this step is, you feel like this is tight. You feel like most diagrams probably are of the form mu plus box. So you don't feel like you're losing too much there. And I guess you're not losing too much in Cauchy-Schwarz either, just because we have a matching lower bound. Okay, so I'm gonna like do a couple minutes of summary at the end, but before we do that, are there any questions? This is like the whole proof. It's a famous theorem that you're seeing right now.
By the way, we said at the beginning that there is just an increasing or a decreasing subsequence of size square root n minus 1. It should be square root 10, right?
I think it might be n minus 1.
Let's say 10, right? If n is 10.
Let's take this off. It's square root n minus 1. Let's take it off.
Sure.
Yeah.
Yep.
Let's take it off because it's not kind of good.
All right. Any other questions? Okay. So yeah, let me.
Actually, can I ask one question? Is this how it was originally proved, or is this like a modern?
I actually don't know how it was originally proved. So yeah, this fact was originally proved in 1977 using like much more complicated analysis of the RSK algorithm. So this RSK algorithm has been around.
But it was still using the RSK.
Yeah, RSK has been around since, actually it's around since like 37, I think. That was Robinson who initially introduced it, but it was like he was a mathematician, didn't write it very well, nobody really understood what was going on. Then Shenstedt came along. Shenstedt's the guy who looks interesting in the picture. He came along in 1961, and he gave like this modern form of the RSK algorithm that you see here. He proved the RSK bijection, and tied it in. So the fact that like the length of the first row was equal to the longest increasing subsequence, that's called Shenstedt's theorem. Knuth came around later and like substantially generalized it. Instead of permutations, they're like matrices. And we don't use the generalized form anywhere, but for whatever reason, they tend to call even this simple thing that Shenstedt proved, the RSK algorithm. But yeah, ever since like 1961, basically almost every theorem about random permutations, random words, and their longest increasing subsequences have all gone through this RSK algorithm. For example, the lower bound. If I want to get lower bound by 2 root n, I know no proof that does not use the RSK algorithm. Okay. That's the upper bound. let me just tell you a couple of other interesting historical notes. So we just showed that L sub n equals 2 root n. But you might also ask, like, that's only the higher order term. What is the next lower order term? Another question you might ask is, what is the standard deviation of, you know, LIS of pi? And most people, I think it was conjectured for a while that, well, the highest order term is root n. So oftentimes, you know, if root n, or if you have like some higher order term and you want to figure out what is the natural standard deviation to associate with it, it's probably the square root of that. Okay, so people conjectured that the standard deviation is like n to the 1/4, and then maybe they also thought that the next order term was also around n to the 1/4. Not only that, like the natural thing to assume is that what is the distribution of these longest increasing subsequences? Well, probably for a very large n, it's like 2 root n plus some sort of Gaussian noise. Okay, so this was a conjecture. And this was actually proven false. So originally in like the early 90s, people started running, they got better and better computers that could actually simulate longest increasing subsequences. And they found that if this thing should be around n to the 1/4, they actually found that this is false. Numerically, it looked more like it was n to the 1/6. Both of these.
That's still a conjecture.
This, yeah, so that was, no, not a conjecture. So then this was confirmed in like 1999. And they found the exact limiting behavior of LIS of pi. So it converges to a nice distribution, which is not Gaussian, but something called the Tracy-Whittem distribution. And basically, Tracy-Whittem is kind of like what you get when you take, let's say, an m by m matrix. All of these are 0, 1, sorry, are normally distributed. And maybe you have some symmetry constraint. Actually, it's really, they're like normal, but they're Hermitian, so there's complex normals, and then you say that it has to be Hermitian, but whatever. So you have an m by m matrix, and then you want to look at some quantity that's basically like, let's say this is x. This is a random matrix, so you might want to look at lambda 1 of x. And the Tracy-Whittem distribution is exactly what you get when you take this, subtract 2 root n, and then multiply by root 2 n to the 1/6, for some reason. Okay, so you pick a random matrix, look at its largest eigenvalue, subtract off 2 root n, multiply by root 2 n to the 1/6. This is exactly the Tracy-Whittem distribution. It's some famous distribution from random matrix theory. And what it was shown was that LIS of pi is exactly equal to 2 root n, well, not exactly, but as n grows large, 2 root n plus n to the 1/6 times Tracy-Whittem. And this Tracy-Whittem distribution, it has like, so its expectation is negative. It's like -1 point something. So that doesn't contradict what we saw earlier. Its variance is also, or standard deviation is also a constant. So you can get like both of these bounds.
So I'm not, so if it's 2 root n plus n to the 1/6 times something of n to the 1/6, you get the 1.
No, so this thing, when I look at this, I subtract off 2 root n. Oh, sorry, wait. N. So this thing right here is a random variable associated with this matrix. And then, of course, I look at the random variable as m goes to infinity. Whatever. The order of this thing is like m to the negative 1/6.
Oh, I see.
So then I take this random variable and I multiply by m to the 1/6, and I get a random variable whose like mean and standard deviation are both constants. And then in which case this thing is like an expectation, a constant, typically a constant. This is somehow like the new Gaussian distribution. So as far as I know, like this Tracy-Whittem distribution is popping up in all these crazy places where like things are, people are talking about like a universality principle similar to the central limit theorem or But people don't really understand why it pops up everywhere, but this is like one of the most famous examples where there's no reason you should expect, these two things to be similar. Actually, it turns out this is, well, it turns out many other amazing things happen.
So just to understand this, the matrix itself, all the entries are Gaussian, possibly you draw two for complex, and the diagonals are...
And like, maybe I want it symmetric, so this one is the same as this. Actually, it's the complex conjugate of that, but...
Okay. Basically, you have like as much independence as you can, subject to...
Yeah. Yeah, a huge amount of independence, and then you're like, but I want to look at the eigenvalues, which may be highly there's like tons of correlations going across there.
Yeah.
Let me mention just one other amazing fact, which is, in addition to looking at LIS of pi, people also like to look at the shape of the RSK algorithm. So it turns out that if I run this RSK algorithm on a random permutation, I typically get a shape that looks like this. Or maybe that looks like that. So that's a permutation of size 1,000. I get some nice shape that looks like this. And people like to, there's something called the the Russian notation, where I take the shape and like rotate it. So this point is down here. And when I rotate it, it looks like this. And it turns out that there's this very nice curve that as n grows larger and larger and larger, it grows like arbitrarily close to this curve with super high probability. This curve is given, it's like 2 over pi arc sine x plus square root of 4 minus x squared, something like that. That was almost right. Weirdly enough, this also has something to do with random matrix theory. I don't really understand this myself, but this curve has like strong connections if anyone knows the semicircle law. This is like another instance of the semicircle law. Anyway, there are more connections to random matrix theory, more beautiful connections to other things. This was like the state of the art in the 70s. Anyway, so that's the end of my talk. Thanks for listening. Any more questions?
Is there an intuitive reason why you subtract out the 2 root m? Because you say like that full term now has order for like 6, is that just to try and get that order?
Yeah, I guess.
I guess you're removing the highest order 2.
Yeah, so this thing probably has expectation link. This is probably an easy to prove fact that maybe VJ knows how to prove. That this thing's expectation is basically like 2 root m.
So essentially, okay, so yeah.
Now one thing I don't know, it's kind of amazing that like you get a 2 root m here and like an m to the 1/6 here. You also get a root n here and an n to the 1/6 here. I don't know if that's like pure coincidence or some amazing deep thing. Like this could be m to the 1/7, right? There's no reason why it has to be a 6 too. But any other questions?
Let's think. Oh,
sorry. So is this thing LIS minus 2 root n times?
Yeah. So this statement is, if you look at LIS of pi minus 2 root n times n to the minus 1/6. This random variable converges to the Tracy-Witten distribution. So they have basically the same form, except you got a minus there, where you don't have it there.
Does this prompt you to think maybe there's like a linear algebraic proof of all this? No?
What do you mean?
Because like you're saying it's distributed like a random matrix, right?
There are proofs of these statements. So, I mean, if you use representation theory is itself somehow linear algebraic. There are proofs of this statement that like switch to quantum. So you can actually, in my talk sometimes I'm like, oh, to understand longest increasing subsequences, you can also understand, it suffices to understand quantum computing. So it turns out there's a proof of this that like switches over to quantum computing and uses things like quantum central limit theorems and whatever. Those might be able to be thought of as linear algebraic.
I mean, like hopefully there's just some kind of matrix you can define on this that's like whose eigenvalue is a proxy for your longest increasing subsequence, maybe approximately.
This seems like a lot easier than analyzing eigenvalues of random matrices.
Really?
Oh, the proof of this, the proof of this statement though, to be fair to VJ, is also very hard. I do not understand.
Oh, but I thought you were saying a proof of the thing that you just showed us.
Oh, the 2 root n, yeah. You can't get any easier than that. But yeah, I mean, sometimes you like multiple proofs of the same thing. Any other questions? Okay, thanks again.
Let's thank Nick. Let's also thank
I'm not Nick, I'm sorry.
Let's thank Nick. Let's also thank John.